Hi, it's Gadget UK here again. Something I've been meaning to do for a while is like a basic introduction to digital electronics. Now at the same time I wanted to play around with the logic analyzer that I got from Alison Charles. And I did mention in my Famicom restores video, I think it was the third part of the 5 Famicom repairs, I was going to get the logic analyzer onto this at some point and show you a few things. But I do get quite one of the most common requests I get from people actually is, wanting to know more about the digital side of things, understanding digital electronics, how you would use a logic probe, a logic analyzer, and just how digital logic works, because some people, I think, they understand the basics of electronics in general. They've got an understanding of some of the basic components, resistors, caps, diodes, transistors, etc. But when it comes to the digital side, there's a few gaps in the knowledge, I guess. So I'm not going to be covering everything. This, electronics is one of those areas that I could spend literally hours just talking about one particular point that I'm going to cover here in literally a minute. The idea is to cover the basic concepts within this video, and I guess at various points there, if you want to know more, you just go off and research, the things that I've said, there's particular topics and things, and you'll find an awful lot more in-depth information on every single thing. Everything that I show that takes a minute to show you, there's several hours or more of research you could perhaps do yourself to, get up to, expert level, I guess, is the point I'm trying to make. So this is just going to be like a noob's guide, or an idiot's guide to me being the idiot's guide to digital electronics. Yeah, so apologies for the background noise. It just seems like one of my annoying neighbours has just decided to get out his chainsaw. I'm not quite sure why. He doesn't seem to be cutting anything with it, just revving it. Anyway, Friday the 30th was yesterday, so he's a day late. I figure the best thing to do is just to start with the basic thing about AC versus DC. So just looking at the differences here between AC and DC. AC, you've got positive peaks there, and you've got negative peaks. And in mains, for example, here in the UK, 50 hertz, 50 times a second, you're getting these changes from a positive pulse, it swings to a negative pulse, and you use that, bridge rectifiers and things to rectify that to DC typically. So on an oscilloscope, this is what you would see. You'd see these positive peaks here, and you'd see these negative peaks, that being sort of like a ground level, if you like, in the middle. Now with DC, you're just going to have a straight line like that, and you're going to have a straight, from your ground. So, sorry, not on camera, are we? This is a ground level. You've got a voltage of whatever volts. So, typically maybe in a spectrum or a NES or something, we might be looking at 5 volts there. That might be the VCC voltage, and VCC incidentally stands for voltage collector. I'm not going to go too much into that, but yeah, that's what VCC stands for, 5 volts. So you've got your logic high level of 5 volts, and your supplies at 5 volts. Your logic high level's a bit lower than 5 volts typically, and I'll come on to that in a second. So looking back at AC again, and in particular RF signals and things, you could have something modulated on this. You might have another signal within there like that, and that would be your typical analog RF type signal that be transmitted for things like TV and audio, whatever. So I guess way back when someone started thinking about the principles behind computing and digital electronics and stuff, they decided that you want 2 states. You want high and a low. You want a 1 and a 0. So your 5 volts here, this would represent a 1, and your ground level, in the simplest example, would be a 0. So we want to just deal with 1s and 0s effectively, and you might be wondering why we'd want to do that. Well, when you've got a signal like this is open to interpretation. You can have noise, things can interfere with it, and you've got all these various voltage levels, and a signal that might do something like that. All of these, sorry, I'm off camera. All of these, the levels here, are susceptible to noise. It's analog, I guess, is what I'm trying to say in the simplest sense. It's an analog signal, whereas digital, it's either on or it's off. It's nothing in between. If it was down here somewhere, that wouldn't register. You've got a problem with your system if you've got a level there bang in the middle. So for for computing, reliability, reliability of data going from one place to another, some system whereby you've just got either a high or a low, you're dealing with constancy, it's one or the other, is a really good thing to have for reliability, and other reasons. So there's so much to cover, it's easy for me to just go through some notes while I'm doing this actually. So in terms of that logic level, we discussed there 5 volts as being a representation of a high signal. Sorry, my cat's trying to pounce on the damn pen now. So yeah, TTL, transistor logic, is what TTL stands for. And I'll come on to logic gates and things in a minute once we just get past the voltage stuff. 5 volts is typically what you would expect as a supply, but that translates, as you can see down here, a logic high on outputs, and it varies between outputs and inputs on a chip. On an output, you would roughly expect between 2 volts and 5 volts. That will class as a high. So you could be measuring 2.5 volts there, on a scope, on a data pin or something, and that actually would register, well, most of the time would register as a high. And the low is between 0.8 volts and 0 volts. Now inputs, it's just slightly different. If you look, a high 2.7 volts, whereas that's 2. So an input needs at least 2.7 volts to be, a high, or up to 5. So you've got a threshold there, is the point I'm trying to make. It's like if we were to draw on here, in fact we've got this here, we've got the 5 volt level, so your logic high might be, for argument's sake, actually the distance between there, let's say that's 2.7 volts, and your logic low is going to be much lower. It's going to be down here like that, between there, so it might be like, is it 0.8, so it could be 0.8 to 0, so your logic low is that small window there, and your logic high is that window there. So that's that covered. Coming back to logic levels again, on more modern devices, as things have got faster and they want to, they generate more heat, you get more heat with more voltage. So what they've tended to do, as things have got faster, voltages have gone down and down and down. So 3.3 volts, yes, a lot of the old retro stuff from the 90s onwards and stuff has got 3.3 volt logic and stuff, but more modern stuff, you'll see it's got 2.5, 1.8, 1.5. I put 1.2, I'm not sure whether there is any 1.2 logic, there may well be. Wouldn't surprise me, we're probably going to keep going lower and lower and lower, probably 1 volt and then half a volt or something, I don't know. So hopefully that's clear about the different logic levels there that represent a 1 and a 0, and why we went down that road really from analog. So the next thing to talk about here are logic gates. Now, most chips comprise of many thousands, tens of thousands, hundreds of thousands of these gates here. And these are kind of like the fundamentals of digital electronics really. Without these, chips and things wouldn't be possible. And these gates actually comprise of multiple transistors. A NOT gate, for example, has probably got as many as 4 transistors in there. There might be other components like resistors and diodes and things, but typically, these gates are made up of, let's say transistors. And that TTL, coming back to the 7.4 series, which is, TTL. There are some, and this is where it gets a bit confusing. In the 7.4 series range, there are some chips that are CMOS compatible. They've got CMOS outputs or inputs or whatever. And CMOS is similar in many ways to TTL. If you think about the thresholds we looked at before with the voltage levels there, CMOS has just got a different higher voltage and it's got different thresholds, and it can it uses less power. It's faster, faster logic CMOS. But TTL is what we're dealing with here. TTL is more common. You do sometimes find a CMOS chip. I mean, Commodore 64s, for example, there's loads of CMOS and HMOS stuff on there, but the principles are the same. It's just you've got different thresholds there. Certainly when you're dealing with something that's powered by 5 volts, they're subtly different. But yeah, so these gates, or if you think each one of a chip, you can get a NOT chip. I mean, an actual NOT chip, a 7.4, say, 04, 7.4 LS04, would contain 4 of these NOT gates, and you can use them however you want. But so how this works, you've got an input and an output. And basically, if we put a 1, high, 5 volts roughly, in as an input here, on the output, we get the inverse. And that's what that line indicates there over the top. invert, if I can write. So yeah, you invert. This is an invert. You know, an inverse whatever you put in there. So a not. So if you were to put a low into the input here, you're going to get a 1 out the other side. So hopefully that is really that's the easiest one to understand. Dead simple. You know, it inverts whatever you put in there. You put high, you get a low. You get low, you get a high. So then moving on to slightly more complex examples, but these again they're pretty simple. They're not that hard to grasp. It gets a bit harder when you get a bit lower down. So the AND gate is as it sounds. These, and that's another interesting thing with these. The way they've been designed, they're very logical in the sense that the names they've used to describe these describe very well their functionality. So an AND gate is what you would expect. AND A and B. So if you were to put a 1 and a 1, you get a 1. If you put a 1 and a 0, you get a 0. Because you need both. You need A and B to get an output, and two lows will still just give you a low. So the only time you would get a high out of here is if you've got a high and a high. It would help if I did what they call a truth table, which is just a little table below with the two inputs and the output, and you can just list down the combinations. You know, if you've got a 0 and a 1, what do you get? If you get a 1 and a 1, what do you get? A 0 and a 0, a 0 and a 1, etc. That's the truth table. So, you know, you could go away and do that yourself for one of these, and look at some of the tutorials out there if you're still not familiar from what I've explained there. But like I say, an AND, you've got to have A and B to get a high out of here. And an OR, again, it should be pretty simple. You could probably work out just from that name OR there what you're going to get. If you've got a high on A or B, you're going to get a high out of here, if that makes sense. And then, you know, zeros, obviously you're not going to get anything. If you've got two zeros there, you're just going to get a low here. So, you know, if you know, it's just like I said, the name gives it away. It really is that simple. And then you can combine logic. So this here means that circle is the invert. Wherever you see that circle, it means invert, just like that line does. So on this gate here, hopefully you should be able to piece together. If you look, we've got a NOT gate. You can see the inversion there, and it's called NAND. NOT. It's a NOT and an AND. So it's combining the NOT functionality with the AND on the output. So basically you've just got an AND gate, but then when you've got 1 and a 1 here giving you a high, that high will be inverted and you get a low. And if you've got no inputs, you know, if you've not got the AND condition met there, you're going to have a high out of here instead of a low, if that makes sense. So it's kind of like, you know, it's inverting the AND functionality. And the same holds true with the NOR. You know, you've got an OR gate, and then you've got a NOT on the end. And then the final example, there is another gate, I think, I can't quite remember now, but the final example, I don't know why it's cut it off here. This is an XOR gate, exclusive OR. So with the XOR, the exclusive OR, that's the easiest way to remember this, is the exclusive part. It's got to be exclusive. So in other words, you can only have one high. If you were to put, that's the only way you would get a high as an output, if only one of these is a high, if that makes sense. Whereas, say, if you just look at an OR gate, for example, it's, you know, either of those is a high will give you a high, but both of them will give you a high. That's all that gate is interested in, is one or the other or both. Yeah. Whereas this one's exclusive. You've got to have only one. Only one of you guys is exclusive enough, if you like, to drive me and give a high output here, and everything else is a low. So it's, you know, if you had that scenario there, 1 and a 0, you'd get on a 1. But if you had a 1 and a 1, this would go, no, it's not. You're not exclusive. There's two of you guys. So you'd only have a low there. So like I say, the only way you get a high out of an XOR is if only one of the inputs is high. That's the easiest way to remember it. It's got to be exclusive. You've got to, you know, exclude one or the other, or it's got to be exclusive, as in, you know, I'm a celebrity, there's only one of me, can only have one. That's the easiest way to remember that. So a point of further study, I guess, at this point, if you want to go away and understand a bit more about how these logic gates can actually be built together to form much more complex bits of functionality, because you wouldn't believe it, but a processor is made from, you know, let's say tens of thousands of these. So I spent a bit of time doing some visual representations of things here, just to make it easier to understand some of this stuff. So if you think of a mechanical system here, now this could be a good example of, say, a water mill. You know, the way a water mill works, if you're not aware, you know, a giant wheel there that's, you've got water flowing past, pushing the teeth, the blades on the water wheel. And that water wheel ultimately, you know, it's a gear, you know, it's connected to another gear, and that gear then's connected to some a belt or something that's moving boxes along a conveyor belt or something. So you get, the point I'm trying to make is you've got power, you've got something coming in, some force, and it translates into a mechanical movement there. So if you then compare to our CPU, here's our 6502, and it's sat there, it's connected on the board, we've got ground, we've got 5 volts. It's like, say, the transistors in there are all sat there waiting for data to flow through it. You know, the CPU's just sat there waiting. It needs something to actually drive, just like we had in this example here, something to drive the processing along. You know, it just sits there idle. And you've probably already guessed, this is where your quartz crystals come in for generating a clock signal. So, you know, you get the piezoelectric effect here. Some bright spark, probably 100 years or more ago, probably worked out that, you know, crystal, these types of quartz crystal, when you slice them and put pressure on them, you get, you know, electricity generated. So these are finely tuned pieces of crystal. You know, they've been sliced and cut and stuff to get the crystal just the right thickness, and you basically, you know, put a low voltage across it, and you get an oscillation like this here. So there's a basic example of this, you know, being powered, just generating some pulses. And you might be more familiar with the 4-pin version, where you give it power and stuff as well, and it just, you know, just outputs a nice clock signal there. But in principle, that's where you get your clock signal from, and you need that to drive your CPU. It's, you know, coming back to the example over here, it's kind of like the water turning the water wheel, which then turns another gear, which, you know, gets your factory going. You know, it's driving all the machinery. And there you go. There's a really cheesy example there of our, you know, what's previously idle, just doing nothing. You know, it's got its ground, its power. Now it's got a clock signal, it's doing something. So here's the next step of this here. I'm going to just, you know, go into a little bit of detail about, you know, what's internal to a CPU and how it works. So as you can see, read instructions from address, process instruction. That's typically the sort of thing it will do. Read an instruction from address, process it, read the next one, process it, read the next one. So, you know, it's like, say, and it's happening. Those steps happen in sync to these clock edges. Now, it's not necessarily like one pulse, one instruction, one pulse, one whatever. It could be a number. You might have, you know, 4, 5, 6, 7 of these clock cycles here before it actually reads an instruction, before it processes an instruction. It's going to vary from CPU to CPU. I can't quite remember the cycle count there, and it varies, I think. Some instructions take more of these clock edges than others. So you don't get, you know, it's not a totally linear processing. You know, you don't get it's not exactly linear. You've got some things will take longer than others. You know, for example, reading from RAM might take more cycles than something else. So I'm not sure on the simplest way of explaining some of this stuff, because there's an awful lot to this, and I want to try and just cover it in as basic as detail as possible, really. But you get registers within a CPU. You know, what is a CPU? Well, it's this black, you know, this black box here, and if you imagine within it, it's got these this particular one, 6502's got these 6 register blocks, if you like, chunks of functionality sat inside there. One of them is the status register, and it's 8 bits. Now, I'll cover that first, actually. You can see here, these are the bits, yeah, within that register. So, if you look at, say, bit position 0, for example, it's marked C. C is carry. So what that indicates is when it's done an arithmetic operation, you know, it's added a load of numbers, or it's done a division, or it's done something, yeah, you've got the processor wants to indicate to you, as a, you know, a user running code, I'm having to do a carry, yeah. That's what that indicates. So if that bit was set in the status register, you know that it's indicated it needs to do a carry. And it's it's the same with all of these. What bit position 1 there is Z to indicate 0. So for example, some of the instructions the CPU can do, you know, when you give it code to do various things, one of them is to, can you tell me, you know, you want to know whether the value that's something it's just done or something it's looking at is a 0. That will indicate it's a 0. And you've got one there to disable interrupts, I think. One to put it in decimal mode. That's going to be to do with any math stuff you're doing. Break command. I've never used that. I'm not sure what the break command is. That might just indicate it's hit a break command. I'm not sure. V to indicate an overflow. So again, if you've given it some arithmetic operation to do, adding some numbers. If they've overflowed, you want some way, as a programmer, as a developer, or whatever, to know that that's overflowed. That's what the V's for. And obviously, it's the same with arithmetic negative. If you've subtracted some values from each other in the CPU. You want to know whether you've got negative value. So that's the purpose of the status register. I'm sorry it's probably as clear as mud at this stage, but nevertheless, like I say, just imagine each one of these as a little chunk of functionality sat on the CPU, and these are integral to the 6502. Different processors will have different registers. They'll all typically have like a status register and a program counter, maybe and a stack pointer, but then these ones here, they'll vary. So this is more of an example of a CISC type computer, a complex instruction set computer, I think this last final C's computer, CISC, yeah, CISC. But some of the more modern devices and things like were RISC. I mean, a 68000 is probably classed as a RISC processor. It might not be, but a 68000's got an awful lot of registers compared to these three. These are general purpose ones here: X, Y, and accumulator. So the accumulator is where you stick things to do with, if you want to add something up or subtract things, they'll go in the accumulator typically, and the result may be in the accumulator, I think. And then the X and Y registers are general purpose registers, and I'll come on to that a little bit later on once we actually look at some of what they call opcodes. So your program counter and your stack pointer are also, really important functions of a processor like this. Your program counter, what that does, that points to a specific area in the address of the CPU address space, and I'll come on to the address space next because all will become clear, and then we'll just come back to that and revisit. So one of the main uses of the stack here is as your processor is going through processing instructions, at various points it can get interrupted. It can just I'm running some code here, what's the next line of code? Suddenly it's been interrupted. One of the pins on the CPU will typically be like an IRQ, non-masculine interrupt type pin or something. So the hardware that's connected to that in the system can raise an interrupt by maybe pulling that interrupt pin low, which stops the CPU doing what it's doing. The CPU will push things onto the stack there, anything it's working with, like the return address, for example, of where it was up to. I'm up to line 500, for example, in the code, address 500. I'll push that to the stack, so it gets stored in RAM typically. The stack area will be in RAM, and then the processor then services the interrupt. Whatever that interrupt was, it'll have an address associated with it, and it'll shoot off, run some code, and when it's finished running that code, it returns back to the stack and pops off the program counter or whatever data it's had off the stack, and is then able to continue processing from where it's at. So that's where your stack comes in. It's as it says. If you imagine a stack of plates, it's like you've got 3 plates in your hand. You're dealing with that third plate, that top one. Somebody else comes along, gives you a 4th plate. They stick it on top of that. You're now dealing with the 4th plate. But once the 4th plate's been done, you're down to the 3rd plate. That's the easiest way to think of the stack. It's a way of being able to work on multiple blocks of code, if you like, in a logical, sequential way. And as I mentioned before, the accumulator, it's just another one of these registers. You can stick a number in, you might stick a 7 in there, and then you might do some arithmetic operation, subtract it from a value at address X. X might have an address in it, and it'll go away and it'll do that arithmetic, and it'll probably leave the results in the accumulator. You might have a 1 in there. You start with a 5 or a 6, now you've got a 1 because you've done some arithmetic operation. So that's what your accumulator is used for. So it's used in conjunction with the X and the Y index registers here, and these are just ways to address memory. So you have specific instructions that say add something or compare something between the accumulator and a certain address, and this is how you specify the addresses using these X and Y registers here. So coming back to this block diagram here, your CPU needs to obviously read and write to your RAM, and it needs to read from your ROM. So how does that actually happen? Well, you've got a data bus in order to actually get the value. Either send a value to RAM. If you want to write the value, let's say 7 to RAM, an address in RAM, you need 8 data connections between the CPU and the RAM. So as well as your 8-bit data bus there, and that's what the bus, your eight lines for your data connections there, that's classed as a bus. So you've got an 8-bit data bus for writing, reading or writing, a byte at a time from RAM or ROM. You could actually write to ROM. Nothing's going to happen because ROM is read only, but it's worth pointing that out. In fact, some protection mechanisms used to work that way actually. The CPU would just every now and again write something to ROM. So if you were a hacker and you'd copied a ROM game into RAM and tried to run it from RAM, when the CPU occasionally tries to write to what would be normally ROM, which wouldn't do anything, it would write to RAM and corrupt your code. So yeah, that's something interesting for you. In fact, the VIC-20, that's the VIC-20. Some of the cards of the VIC-20 did that. So yeah, we've got the 8-bit data bus, 8 data lines there for holding our bytes, in either direction. You also need a way to specify where in this RAM you want to write to or read from, and the same with the ROM. Where do you want to read from? So you have the address bus. Now the 6502 has got a 16-bit address bus, so that gives us 65536 addresses that we can read and write to. So here's a really basic example. If you imagine this, these like pigeonholes. If you think of like pigeonholes in the old hotel lobbies and things, where they would have mail for various people. It's like a mailbox. You've just got this matrix here of boxes, and from side, this way across, from left to right here, this is our data bus. We've got 8 of these, 8 bits. Each one of these will hold a 1 or a 0. If you think back to what we covered about highs and lows, each one of these blocks in memory here are going to hold a 1 or a 0. And each one of them represents a number, if you like. So like the first bit position there represents 1, the next one's a 2, then a 4, 8, and these double up as you go. Each time you double 8, 16, 32, 64, 128. So the last one there is 128. I'm sorry they're not very well aligned. I could have tabbed this all out. It would have took ages. I can't be bothered with it. So yeah, you've got 1, 2, 4, 8, 16, blah blah blah. And if you were to add up all those values there, you'll get 255. So that's where your 8-bit limit of 255 comes from. It's a possible. The maximum possible value of all those bits being set to 1. If you had 1 on every pin on your data bus there, that's what you would be representing to 255. It's all those numbers added together. So you can get obviously in between values here. If you wanted just a 1, value 1 is on your data bus, you'd have a 1 there, and all the other bits would be 0. 3 would be 1 and that second bit there. So you add them together, 2 and 1 equals 3. So those first 2 bits would have a 1. And then obviously, let's say for each byte in memory, you've got an address associated with that all the way down here. And these addresses, I'll probably have to scroll down a bit because it's not going to be fitting on the screen, I don't think. They go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. As soon as you get to 9, you're on to A. Now this is hexadecimal. So instead of decimal, where you count from 0 to 10, you've got 16. So as soon as you get to 9, 10 is represented by A, 11, B, C, D, E, and then F's 16. So you've got 0 to F, and then after you've got to 16, you've got 1, 0, and it continues 1, 1, 1, 2, 1, 3, all the way up to 1, 9, 1, A, 1, B, 1, C, 1, F, 2, 0, etc. So that's the way we represent the address numbers, if you like. There's been a lot more zeros, leading zeros, for an actual address. This is just a simple example here, and of a really small list of addresses. And like I say, for each address, you've got 16 data lines. So actually, your maximum, I'll see if I can, I might as well just type this on here. Your maximum address value for 16-bit is, so I've got a lowercase f there, haven't we, is FF, and that equals to 65536, I think. Might be 5. Yeah, I think 65535. So, yeah, that's 16-bit. And like I say, when we looked at the data bit above, the maximum value there was 255, and 255 equals FF. So hopefully you can see from that your data bus, the largest value you can deal with is 0 to 255. Yeah, anything between 0 and 255. That's what you can store in the data bus using eight connections there, each with ones and zeros. That's the most you get, 255. With 16-bit, obviously it's double, and this is useful, I guess. You can see it's doubled up, so you've got twice as many hexadecimal characters there to represent that, and with that combination, it continues on. If we look back at this here, where we stopped at 128 on 16-bit, the next one is obviously a multiple of that, so it'd be 256, 512, 1024, blah blah blah, until you get to, let's say, 16 bits. And with 16 bits, the largest value, if you add up all the values there, if they're all high, you get 65535. So in that example we had before there, we had our clock coming in, we had our VCC and ground, so the processor is capable of doing something. Typically what you have is a reset. There'll be a reset on that processor that happens automatically, just usually via a cap or something on there, so that the CPU is reset. And when the CPU resets, what it does, the first thing it does, it sets the address lines to the reset vector. So you have this little table of vectors here, and this is common with 6502. These addresses here, I think, are the same on all the different versions of the 6502 that are out there. First thing it will do when it's reset, it will jump to FFFC, and it will read a 16-bit address value. There's going to be 2 bytes there, those two, FFFC and FFFD, which contains the address that the programmer specified he wants to start the CPU running code from. So, for example, the code could be somewhere else. There could be an address in here that points to somewhere else in your ROM, but that's what will happen. It'll reset, it'll read the address from there, and it'll start executing code from that address. And then you've also got, as I mentioned before, about interrupts. The different devices in your system needing to be able to interrupt your CPU and go, whoa, stop doing what you're doing, I need you to do this is urgent. You get your interrupt signal. The CPU will then jump off to these, depending on the type of interrupt. Is it a non-maskable interrupt? Yeah, it is. I'll jump to FFFA in the cart, and there'll be 2 8-bit values in there that specify what address in the in the ROM I need to go away and process as part of your urgent request there. And the same thing, for an IRQ or a break vector. Say there'll be an address, 2 8-bit values at these locations here in ROM typically. So that if an IRQ occurs or a break occurs, the CPU will shove what it's doing on the stack, say, right, okay, I'll stop doing that for now. Now I'm going to jump off to this, look at this address here, see what's in there, what's the address, where do you want me to go, what do you want me to do. So then something useful to have if you're designing a CPU-based system is an address map. Something where you can see the ranges starting and where it ends and what it actually relates to. So that's what we've got here. This is for the NES or Famicom, and you can see from address 0 to 7FF, which is, and that represents, obviously it's hexadecimal. That represents a size of 800, which is 2K 2048. If you convert that in calculator, hex value of 800 to 20, it will convert to decimals to 2048. So you've got 2K of RAM. That's where your 2K of RAM sits in the address range. So what you'd have to do is, physically on the board, there will be address lines connected to that RAM for that range, if that makes sense. And then at 800, you've got the same thing. It's mirrored. So it's a convenient way of the programmer being able to write to an offset address and still write to the same place. I'm not quite sure why they do that actually. It's an interesting. I've heard in the past that you can get performance benefits from using mirroring. I'm just not sure. I can't think of an example. If I look through some of the cart code there and disassembled some of it, we might be able to find an example of where it's beneficial. But that's all they've done, is they've plugged a gap there with a mirror of the original. So if you were to write to 0800, you're writing it effectively to whatever's at address 0000. So you're pointing to that same RAM. And again, if you were to write to FFFF, you're writing to 7FF. So yeah, that's what mirroring is. Now, strangely enough, I can't quite remember this, but there's nothing there at these 2 addresses. Those seem free. It may be that some carts plug in VRAM or something in that address range. I'm not sure. I can't remember. And then at 2000, you've got your PPU, which is the picture processing unit. That's what PPU stands for. It's your graphics chip. So if you want to draw to the screen, change the screen color, draw some sprites, etc., it's all done via communicating with the PPU between 2000 and 2007, and then it's mirrored, just like the RAM was, between 2008 and 3FFFF. There's quite a lot of mirroring there. It's a large chunk, because you only got like 8 bytes if you look at that address range there. We've got 8 different registers you can write to, but then they're mirrored a number of times, and it says there, you can't quite see it, repeats every 8 bytes. And at 4000 to 4017, you've got the APU, that's the audio processing unit, or PAPU as a lot of people like to call it, the pseudo audio processing unit, because it's not really a separate unit, it's just some registers with some analog circuitry that sits on the CPU die there. So it is integral, it's internal to the CPU. If you've got a CPU fault on a NES, your sound's gone as well, or if you've got a sound fault on your NES and it's not something to do with the output stage of your sound, it's actually the sound that's coming out of the processor, you need a new processor. And then you've got some more APU and I/O functionality here, I think probably for the controllers and stuff. It says it's normally disabled. That's interesting, I can't quite remember that. So your cartridge space sits at 4020 up to FFFF, and bear in mind, let's say we need it to go to FFFF, because that's where, if we just scroll down a little bit, that's where our reset vectors are, just around that area there, FFFD. So it's important that the cart sits within that area, so that when you boot the system, it's going to, first thing it's going to do is read something from the cart and start execution from the cart. Now in other systems, obviously these things get a lot more complicated, because sometimes you have an onboard ROM and it'll boot from a ROM rather than the cart itself. I mean, that's what I like about the NES and the Famicom. It's booting straight from the cart. There's no onboard system ROM to do with protection and having system I/O functions and things built into a ROM, etc. that can just make them harder to work with and harder to learn. The nice thing with this is it's just a CPU connected straight to a cartridge, ROM, and it runs straight from the ROM. It's running raw, 6502 code there. There's no protection or anything going on. So here's a quick look at the emulator I wrote many years ago, actually. The debug functionality is the thing I found most useful when I developed this, really. So you can see the CPU here, we've got the accumulator, that's showing what's in the accumulator at the moment. We're showing what's in the X register, the Y register, the program counter. I think it probably, when you first power one of these CPUs up, it defaults to C000. I can't remember what IR is for now. What's IR? Yeah, pass on IR, I can't remember what IR is. Status register and your stack pointer. Yeah, and I'm not going to cover it in this video, but I also added some stuff here for the PPU so I can see what values are in each of the PPU registers there as well. And on the right hand side here we've got a very small window into the memory. We can see where it's looking at, the program counter's point to C000, and at C000 we've got D8, so that's going to be an instruction, it's going to be an opcode. That's what the CPU is going to do first, it reads an instruction. What do you want me to do, and then sometimes you get a value more often than not. So some instructions will you'll need a value, as what they call an operand, and that'll follow on at the next byte, the next address there. So I suspect that's going to do a D8 with the value 78. So if we just have a quick look at the source code for this. So, sorry, I know this is totally zoomed in here, but what I wanted to show you is the values in your ROM. You've got a D8, we saw a D8 there, that byte. It's going to represent an instruction. I know that because that's the first byte it's going to try and run. It's going to be an instruction, so the CPU needs to, first thing it'll do is push an instruction, read an instruction into the instruction register. That's what IR was for. My mind was blank at the time. So it knows what to do. What do you want me to do? Well, the first command there is, the first instruction is D8. So as you can see in my emulator here, all I'd used was a case, what they call a case statement there. So we're reading the instruction register value, and depending on what it is, we do a certain type of instruction. So let's just go down and see if we can find D8. Yeah, there we go. So D8. So the first thing it's doing, this code, is it's going to clear decimal mode. So what you would expect is, do you remember there's a decimal flag? If I just pop the emulator back up here, we've got their decimal, you can see that's set to 0. It's just going to set that to 0. It's already 0, but it's just like probably a good to do when you're booting the system for the first time. So let's see if we can just do that now. We'll just step into that and just see what let's do. And I think if we do step there, yeah, so we've done one single step there, and the decimal flag is still 0. Now the interesting thing is 7/8 is another instruction. So that particular instruction, it didn't have what they call an operand. It was just a single byte. You know, some instructions can be single bytes. Some of them can be have an operand, you know, which follows, which may be 1 byte or more. I think probably only 1 byte. I think on this system. I can't quite remember. It's been I don't know 15, 20 years since I looked at this. Year 2000. I don't know, 18, 17 years ago. It's been a long time since I looked at this. I can't quite remember until I refresh myself. But as you can see, the next thing we've got there is a 7/8. That's going to go into the instruction register. In fact, you can see. In fact, it's still looking at the last instruction here. We haven't actually carried out the see what's in the instruction register there. See D8. If we do another step, dink interrupts. Did that interrupt just change? I'm sure it probably did actually. I'm not sure. I can't quite remember. I never saw that set. But anyway, the decimal flag is still 0, so that's right. And the next thing in the instruction register is 78. So if we shoot off to the code again, and I'll just find out what opcode 78 is. So 78 is disable interrupts. Now I suspect what's happened. Yeah, I suspect this is doing this as the thing's landed in there. So I think in terms of emulation, I think that interrupt flag going high there was as soon as 78 landed in there. Let's just do next step. And bear in mind the next instruction here is AD. Let's just do next step. Yeah, AD. We've got a 0 in a 1 in the 0 flag there. So let's just have a look what AD is. So AD here is load accumulator absolute. So that's going to stick a value in the accumulator, and it's going to be an absolute address. And as you can see, this takes 4 NES clock cycles. So this is what I was trying to explain before about how different instructions take different number of cycles. You know, if you think about that little clock edge pulsing in and out the CPU there, it's going to take 4 complete cycles from positive, you know, from a high to a low there to push that data, that, you know, to do this, carry out this instruction. You know, if you think of the mechanical analogy again, if you think of, you know, some teeth involved inside there turning various parts around, it's like a mechanical operation that's going to take, you know, so many of these teeth moving across. You know, it's like four cycles to run this particular opcode or instruction. So if I just reset that there, you can see those first few steps of execution there in a bit more detail really. Just watch the interrupt flag here as 0. As soon as we get the, we do the D8 first of all, which I think sets decimal to 0, which is already 0, so that will just, we won't see any evidence of that. There you go. As soon as 78, which is the next instruction here, lands in the instruction register there, once we do a step, just watch the interrupts, it'll disable, there you go, disabled interrupts I think. And then AD is our load accumulator absolute. Now I think it's probably going to be taking the address there, it looks like 2002 is it, I think. It's these 2 bytes here, we've got, yeah I think it is, I think that's the way that's working, it's going to 2002. So if we just do next step, let's just have a quick look at the accumulator. It's set to 0, you can't quite see that actually. Yeah, the accumulator up there at the top left is set to 0 at the moment. It's probably still going to be a 0. Let's just do next step. And bear in mind the program counter is at C00002. That's probably going to jump up to C005, I think. Yeah, there you go. So it jumped to C005 because that particular instruction had 2 bytes as an operand there, which was that address, you know, 2002, I think. So the accumulator is 0. It's probably reading from the PPU here, I think. I think that's probably what's happened. It's probably pulled the value out of the PPU. So let's just do next step. The next instruction there is a 10. So let's just have a look what 10 is. So 10 is branch if plus. So this is going to look at the status register. This instruction looks at the status register and checks whether we've got whether the negative flag is set. And if not, it's going to branch. It's going to jump off. Yeah, branch if plus. If it's a positive, it's going to branch off to a relative address. So it's an address relative from where we currently are. So you can see that's the instruction. It's going to run that 10, and it's going to be relative. So in terms of the relative, I suspect it's going to be that value there, FB. It could be A2 FB. I'm not sure. We'll soon see. But the negative is 0. So that is a positive there. We've not got a high there, so it should do the branch. So it'll be interesting to see where it branches to. It could be FB8. Let's just see where it goes. Yeah, so it's at C005. I think that's going to go to C002 next. Yes, it has. So we've got our AD again. Then it jumps to C05. We've got the same condition, the same, check the negative value there. We've got a little loop there that's just going around. It's just looking for the negative flag being set. So if we just step through that a number of times, just keep waiting for the negative flag. The negative flag should get set at some point, and it should break out of this loop. You can see it's doing the same thing. It's all it's doing is checking it, checking that flag, waiting for that negative flag. So you can see there, that's finally, I put a breakpoint there on C007 and let it run through that loop there, and eventually it broke out of that loop and continued processing from C007. That's the next program counter. And the reason that's happened, can you see down here, scanline 240? It was waiting for a hblank, so it was waiting for the graphics chip. That loop of code there, was all it was doing was checking the PPU to see if we'd got to the end of the refresh of the page, if you like, of drawing the screen. And so the next instruction here now is going to be A2. Let's just have a look. What's this going to do? Yeah, so I think this should now continue on from C009. Let's just step that. Yeah, so that's now broken out that loop. It's gone to C009. And I think what's going to happen here, E8, if we look at that instruction, it's STX, it's store X in memory absolute. So we've got an absolute address which is going to be passed as 2 operands for this instruction, 2 bytes, 16-bit address, and it's going to store X at that address. So I think what's happening here, if you look at the value, we've got E, that's the opcode, the instruction that's going to go into the instruction register, E, that's the next code we're going to run, E8. Sorry, 8E, I'm getting dyslexia, 8E, and its operand is these 2 bytes here, so, and the reverse order, so it's going to be 2000, which is the address of the PPU. So, and if you look at, and it writes register X, if you remember right, which is a 0. So I think this is initializing the PPU, this is what's going on. If we hit step, yeah, that's going to put 0 in the PPU. I'll just see if I can get the PPU view up, hang on. Yeah, so there's the PPU view, and you can see what it's doing. It's writing 00. Now it doesn't need to, and this is the PPU, this is the VRAM. The VRAM sits at the address we're writing to here. This is all VRAM, all these addresses here are VRAM. So you can see what it's doing. This code, it's done nothing more than disable interrupts. It's waited for the hblank there, when it's displaying when the PPU is displaying the screen. Probably for certain reasons, you probably need to do this at a specific time. If you start trying to write things in here at a certain time, you might mess up the graphics and stuff, So that's what they've done. They've waited for a hblank, and then they're starting to initialize the PPU VRAM here. So 00 would have gone into that address. I don't know whether we can change this. No, it's a shame I never added the functionality there. So the next step, it's going to do 80 again to 2001, so another PPU register there. So it's probably just initialising those 2 registers, I would think, 2000 and 2001, with the value in the accumulator, which is 0. So if I step, it's going to do that, and then it's going to jump to C00F, I think. The interesting thing I'll point out here, can you see how many cycles? Those are how many clock cycles have run at this point. So you can see just how fast these things run. And this is just the very, very, very start of the code here of initialising the PPU. And look how many instructions have run. So you can imagine, this is why sometimes it can be quite hard to work on these things, certainly without a debugger like this, breakpoints and things on it. Stepping instruction by instruction, you'd be here forever doing manual steps, waiting for that number of instructions to run. But nevertheless, if we, that's going to do the same thing. It's going to put 0 at 2001. So if we just do a step, and then it should jump to C00F, I think. Let's do step. Yeah, C00F. So we've got a different instruction now. So it's written those 2 values. It's written 00 there to 2000 and 00 to 2001, and we've now got CA. So let's just have a quick look what that opcode is. So CA is decrement X, which is interesting. So we should see the X register, reduce in value. If we just go back to the code. So X is 0, 0, so if we do a step, and I'm guessing the next line of code will probably be C010. Let's just do a step. Yeah, it is C010. And you can see what's happened here. We've got a negative situation. I think that appeared. I can't quite remember now. But the X register has gone from 00 to FF. It's rolled round. It's gone back from 0 to FF. And then the next instruction is 9A. So a 9A is transfer the value of the X register to the stack. I think is that. Yeah, the stack pointer gets register X. Yeah, so the stack pointer. So we're changing the stack pointer here. So what I've tried to demonstrate there very, very badly, I appreciate it's pretty crude and stuff, I've probably made a few mistakes and things along the way, but I was trying to show you how the CPU, integral to it, it's got these components, it's got these registers, and how it links to, read the ROM via the address bus there, and it reads, the instructions in there into the instruction register, and you can see the program counter, which points to, which instruction, where in the address space it's going to get its next instruction from, and the status register, and how some of the opcodes there look at the values of certain bits of the status register, to see if the interrupts are enabled or disabled, or see if the the negative flag set, etc. And what that very, very small excerpt of code we were looking at as doing was initialising. We saw the bit there, it was initialised the PPU, it's writing 0 to address 2000, 2001, which is exactly where the PPU sits. I could have gone on longer and expanded a little bit more, but it just takes so long. But what it then does is then it initialises, I think it initialises the stack, it sets the stack to zeros and things, and it initialises the RAM, the work RAM. And then you get some variables and things stuck into work RAM. And it uses the PPU there to specify which sprites to draw. And then at some point you'll get this, the title screen actually displayed there. And it'll start polling, looking for inputs. It reads the inputs there to see whether certain buttons have been pressed, etc. And if they have, it adjusts a value in memory to to say you've selected the next, the second option there rather than the first one, or if you've pressed the start button, it then goes into some different code to start the game. So hopefully there's been enough there just to show you a little bit about how a processor like the 6502 works. And the processors are very, very similar. They just have, let's say, different number of registers, and they just work in subtly different ways. And hopefully you've been able to see there the relationship between the number of clock cycles and the instruction. Some of them take longer to process, based on whether they've got an operand or not, or what they're actually doing. And the other thing worth pointing out while I'm here, the colours are all messed up because this is 256 colour mode, I think, trying to display on a a more modern screen. I think I developed this on 98 actually, and it was part of the MU school stuff. There was a guy called Chris Teague, did a load of stuff in C++, I think, and various people joined the sort of group he had there and worked the way through developing on different platforms, and I did it on Delphi at the time. It took an awful lot of effort actually, because it was the first time I'd dug into anything that low level, and you can see here the speed is absolutely ridiculous. Back in the day this was running at 30 frames per second, I think. If I do display the frames per second, you'll see down here 400 almost 400 frames per second. So yeah, there's been a big change in technology since when I originally wrote this, and it was pretty basic. It had some support for basic mappers and things. It didn't have sound, although I did have a version with sound. I've got it on CD somewhere, but it's really crusty. The way I started to do the sound, and the reason it was so crusty, was I was trying to, I think I had like lookup tables for the shapes of the waveforms, and I had some issue where cutting from one frequency to another, I didn't have clean, the shape wasn't clean. If you imagine a triangle wave and then you're going from one frequency to another, you want to ensure that the point where you change frequencies, you've got a smooth sort of transition that would be representative of what an analog triangle signal would look like, your triangle wave signal would look like. Was its change frequency there, and it wasn't quite right, and there was a lot of frequency manipulation there to get the sounds, so it sounded bloody awful. It was really crackly. For that reason I kind of stopped at that point, because there was loads of way better NES emulators out there, things like Nesticle and stuff, But this was just a learning experience for me back in I don't know 1999ish. So again, this is quite a crude demonstration. I just wanted to do this anyway because I wanted to play around with this logic analyzer of Ali's. You can see there it's a logic analyzer LAP something or other from 0 plus. If you want to know more about these, I think Dave Jones on the EEV blog did a great video on these recently. The software's a bit basic, as he did point out on his video. As you can see, I've got a capture there. I'll do another capture in a sec just to show you. But what we've done here is this has got it's a 16 channel logic analyzer. So it's got 16. I'll see if I can show you 16 of those little pin header type things there, and you just connect up some of these test clips here. So I've got the first 8 connected to the data bus, which is the connections here, 8 connections there, and then I think the clock is the one next to it, the 9th connection there. Black wire, yeah. Is it black? No, it's red, I think. Yeah, red. I use a red wire for clock, and the clock goes into a dedicated clock pin on there, and the ground is brown, and I've got the ground connected there. So what we're looking at here is just the data bus with the clock. Obviously it needs the clock, and then I've put an additional trigger going to bank B, because this is like the first 8 is used for the data bus. Bank B is not used at all, so I've used one wire there, the white one, going to the reset pin. And then what I've done on the software, if I just point you at the screen, you can see, well, hopefully it's not very visible. This is the pin I've used for the reset, B0. I mean, I could change the label there just so it's clear as to what that is. And then the other thing I've done is I've selected all these first 8 the data lines here and right-clicked and said create a bus or something. So I've got a bus 1, and that's what this is at the top. That's what these values here are, showing me the hexadecimal representation of that bus as a whole. So you can hopefully just see a little bit of what's going on here. Now, the thing I'm not sure about is this capture I've just done here was captured from reset. So after reset, we've got some stuff on the data bus that I wouldn't expect to see. That could be, I don't know why that is. There could be numerous reasons for that. It could be something else is writing to that data bus. It could be the CPU's just writing some random crap there as part of its reset process. I honestly don't know. But the bit I'm interested in, I've copied the just the first few instructions we were looking at there, or not the instructions, because some of them are operands actually. Sorry, you can't quite see that, can you? So I've copied the first number of instructions and operands and things, because not all instructions, I think 1 or 2 of these are operands of the instructions. But you can see that's what we saw when we stepped through it, from a reset. We saw D8 and 7.8 AD. That was an address, I think 2002 was it? I can't remember. And then 10 FBA2. So as you can see, if I just zoom a little bit, excluding the crap that's at the start of the capture there, and like I said, there'll be another reason for that, I'll explain in a minute. The first thing we should be looking for is D8, and as you scroll along here, you can see we've got D8, and then a 7.8, we've got 7.8, then an AD. So we can see the bytes being read out of the ROM there by the CPU, AD, what followed AD, 02, and then 20. So you can see the exact sequence of it reading the ROM as it processes, and there's going to be gaps like this as it's doing something else. It may well, some of these things, the capture there is not going to correspond, entirely with that, because of what else the CPU might be doing the bus. For example, at this point here, it's probably writing 00 out on the bus to the PPU, I think, if you remember back to the code we were looking at. I think that's right. Then we had 10, yes, that's right. You can see, sorry, I'm jumping all over the place, 10. Yeah, so that would have been a write. And that's where the read-write pin comes in. I could have, I could add an extra one of the wires here going to the read-write pin, and then just maybe filter out the stuff where it's reading from RAM or writing from RAM. There's and address lines as well. That might be another thing to do, is stick some of the extra connections here onto some of the address lines. I'm just trying to show you the principles behind this, really. And if you play around with a logic analyzer like this, something like this is sufficient for the job. The other thing you want to take notes of, and I'm not an expert at this, but yeah, increase your capture size here as large as possible. think about what you're triggering on. Like I say, it took me a while to find something decent to trigger on, but reset was the best thing. I'll demonstrate that in a minute. And then set your frequency up here quite high compared to what you're trying to capture, just to make sure you're getting a nice clean capture. If you get too near to the frequency you're trying to capture, you won't get clean edges, and you might get misinterpretation, I think, as far as I understand, on some of the values that come back up here. So what I'm going to do to demonstrate this is I've set it to go off reset. So if I hold reset, and I'll just point you at the screen while I'm holding reset down, and you should see in the bottom right there, it should press the start button to trigger. You see it says wait. You can see that in the bottom corner there. It says I'll see if we can zoom. Yeah, it says wait. As soon as I release reset, it's done a capture. If I zoom out now, because my capture window is quite large there, I've set it to 256K. You can see all this red and yellow stuff here. This is where the capture is. So if I just scroll to the right, I'll just point you up a little bit. Managed to use the mouse, actually, it's taking too long to scroll across. I'll just use the mouse. Yeah, you can see there we've got the capture. And like I say, that is representative of exactly what we looked at in the emulator there. So yeah, I mean, I could spend a lot longer going into a lot more detail, but to be honest, it's quite time consuming. You wouldn't believe it's taken me the best part of 4 hours today messing around with the camera and stuff, and editing and stuff later. It's going to take me a while. So hopefully you found that sort of layman's guide to digital interesting. You know, any mistakes and things, please correct me below, and even suggestions. You know, if someone can think of a really nice way to trigger on only reading reads from the ROM, let me know. You know, I did think about it. Like I say, I could just use the address, add the additional wires on there to the address bus, and just monitor that. But then again, it's a 16-bit address bus. You know, so you need 16 connections for the address bus. And bear in mind, my logic analyzer is only 16 channel. You know, you need your 8-bit data bus. You know, I've gone over the number of connections there already. So you can see the need there that you're having the right type of logic analyzer for doing the right kind of work, really. You need like a 32-channel logic analyzer if you're going to do anything professional. You could perhaps get away with something like this, 16-channel for 8-bit stuff, you know, but it does limit you as to, you know, you've got to think careful about what you capture and what you're triggering on. So hopefully you can piece together there from what I've shown enough to understand what I'm trying to convey, really, you know, how this stuff works. You know, starting there from just the logic levels and the thresholds for high and low, you know, and TTL being 5 volts typically, you know, but, you know, the levels you measure probably be a bit lower. It could be 3 volts-ish, 3.5 volts, something like that, 4 volts, but yeah, you know, 0 ground, 5 volts high. And the bit about logic gates, you can understand that, let's say, these chips are comprised of thousands, tens of thousands, hundreds of thousands, millions on modern devices. Those logic gates in various configurations to give you, you know, registers, shift registers, the stuff that processes the instructions, you know, the actual instructions themselves. You know, it's all sort of comprised of those, you know, components that are made of transistors. And then ultimately, you can see the relationship between the CPU and the rest of a system like this. This is a fully memory mapped system, so the CPU can address all the components within there, you know, using different address ranges. And hopefully it was clear there on the address lines, you know, you're using the address lines to specify which box you want out of those little, you know, the individual chips, you know, which block of memory in a ROM or which block of memory in a RAM, which byte you actually want to read via the 8-bit data bus. And obviously it's two-way, you know, you want to write things back using that 8-bit data bus as well. And we saw an example there a minute ago, we looked at Logic Analyzer, where there was a 00, I think, where it was writing 00 to the PPU, you know, that 2002 address or wherever it was. And then ultimately that then leads on to, you know, the logic probe, because that's one of the questions I get asked a lot. How can I use the logic probe? Well, if you think about it, if something's gone wrong with a CPU, one common fault you can get with things like this and any of the chips in here is one of the data bus lines or an address bus can fail. You know, there's a transistor in there driving the logic levels, and that transistor can fail. So you might get a stuck high or a stuck low. So if you were to stick your logic probe on here, you know, the way a logic probe works is you connect your +5 and your ground, and then you just touch the probe on the pin, you know, you want to check. So if you went around the data bus pin by pin by pin, what you would expect to see, you know, bear in mind, you've seen how fast this runs, you've seen the number of cycles that take place just to do those first few instructions when we step through in the emulator there. they're running bloody fast, really, really fast. So in terms of using a logic probe, all you'll see is the probe stuck, because usually two LEDs, a green LED, which indicates a high, and a red LED that indicates a low, and both will be lit to indicate that it's toggling very, very, very high frequency between the two. That's an indication that pin's not dead. That you've not got a dead transistor on the output of that. If you were measuring around those data pins and you found a dead system and you find one that's just stuck high or stuck low and all the others are fluctuating, all the others are doing something, that's an indication it's perhaps that bit. And it might not necessarily be the chip you're measuring it on. It's where you've got to remember that data bus is going to be connected to, like in this system, a couple of certainly one or two places within the system. So you could then use temperature, go around and feel the tops of the chips, use your temperature, your thermal gauge or whatever it is, your IR thing. Check the temperature of the chips. You could measure the currents. I've seen people with specialist equipment where you can put, I think Retro Game Mods has got one of those, hasn't he? A field probe or something where you could just hover over and you can see how much activity is going on a chip. But there's also ways you can measure the currents. I forget, I watched another channel, was it GameTech US? A current probe, you just put it near the VCC pin and it shows roughly how much current's being drawn. So you could use something like that. But generally temperature, inspection, and just thinking about, add a bit of common sense. So for example, if you had a stuck bit on here, what you could do, if you weren't sure if it was the CPU or the PPU, you could just remove the PPU, boot the system, see what happens. Is that bit still stuck? I mean, the system's not going to boot without a PPU, but that bit may then spring to life, and there you go. That's going to be a clue that the PPU, the data bus on the PPU, is what's dragging the CPU data bus pin down. So those are the sort of techniques you would use with a logic probe. A logic analyzer, using it to diagnose a hardware fault, it can be pretty hard. You need to understand the system. As I've sort of shown a little bit in this, you need to understand the operation in terms of the opcodes, the memory map. You need to understand what you're actually expecting to see, what behaviour. So just connecting a logic analyzer onto something like this, it might not reveal anything. If we had a RAM fault now, we would still see all the same opcodes we've seen running to start with, maybe up until a point where something's read from RAM or there's some sort of comparison to something in RAM. But even then, you would need to understand the code that you're actually running to determine that there is actually a fault, and you'd have to step through it, or certainly look at the capture byte by byte to understand where in the boot process it's going wrong. So yeah, these are ideal for reverse engineering, for when you're developing things, diagnosing some complex faults and things. But you really need to have a full understanding and appreciation of the system that you're doing something like this on before you start. I mean, even me, having played around with the NES before, from the emulator point of view, it did take me a good 10 minutes messing around trying to work out a way of just being able to capture those first few instructions there. And I'm still not clear onto why we still see some activity on the data bus there prior to the CPU actually coming out of its reset. And that could well be the PPU writing something to the data bus. It could just be the data bus is floating. There's all sorts of reasons, I don't know. But again, let's say I ain't got a clue, and that shows my lack of 100% understanding of this system to start with. So it's not the easiest thing to use one of these unless you're extremely experienced in the architecture and the hardware of the system you're dealing with. Anyway, I hope you found that rather rushed intro to digital interesting. Please let me know in the comments below. Thanks for watching. I'll see you soon.